All right, we're going to continue to look at what happens when you pull conductors into magnetic fields. So what's happening here is you have this long metal bar that's being pulled this way into a magnetic field that says it's strength 2 Tesla, which is actually a huge field, and it's pointed into the board, okay, represented by these X's. And the first thing we're kind of supposed to figure out is which way the electrons would go in this bar as you pull it in. Well, if you pay attention to a particular electron in the bar, you notice that electron is getting pulled this way through a field that points down into the board. Well, so we'll use a left-hand rule, let's go for electrons. You'd have the electron flow this way, the motion of the electron this way, the field in, and so then the magnetic force will be down this way toward the bottom of this bar. And so pushing down this way would be your F magnetic on the electrons. Right, so the electrons are going to get shoved down when you get into the field. This magnetic force is going to shove electrons down to the toward the bottom of the bar. Okay, so we're going to say the direction of the electron motion is just going to be this way. And what that's going to do is that's going to make this become the negative end of the bar when it's moving through the field, and then that will leave this end as the positive end of the bar. Okay. This magnetic force is given by QvB, Qv perp B, and you notice that all the velocity is actually proportional to the field because the velocity is that way and the field's in. So we can just multiply charge by velocity by the field. And so the magnitude of this is just going to be the electron charge, if we call it E, and then we have the velocity and the magnetic field. So that's going to be the magnetic force on the electron, kind of pushing it down. To get the amount of work done, right, to drag an electron all the way down, work, of course, is force times distance. So the amount of work done is going to be force times distance. Well, our force, we've already found. The magnitude of it is EVB, and then the distance is just the length of this thing, or L. And then final thing on this page is, well, what that means then is if we've applied a force across this distance, we've done so much work. What we can do then is using the idea that voltage is work per charge. Work per charge. And so what we can do is say, well, the amount of work that we've done, we've already derived that. That's EVB times L, force times distance. But then we get to divide by the charge. Divide by E. And so what you find then is the voltage difference then between these two ends is going to be BLV, which is the same that we found when we had a conducting loop that we were pulling in, okay? It's just that with the conducting loop, that voltage difference was able to motivate current to go around, where in this case, there's no loop, there's no path for the current to go. So instead what happens when you pull this in, you just build up this voltage difference, or this what's called EMF, between the edges of the bar, okay? So this is this motional EMF, BLV, when you pull a conductor into a magnetic field.